Hello?
Can you hear me?
Yes, ma'am, I am.
Oh, there's Airman Chung.
I'm sorry I'm late, man. I was having Wi-Fi problems with my laptop.
Believe me, I can relate to that. And Londano. I've been having CAC problems. I have to put my CAC in and wiggle it around, take it back out. Then it tells me it don't like it.
Madonna, can you get Bridges in here?
Yes, ma'am.
Okay, let me see. I see Chung, Hamilton, Londano.
I believe we're only missing Hubbard and Simpson.
Okay.
And Bridges.
Just a couple more minutes. I got Hancock, Malin, Hamilton, Chung, and Londano. Because we got to put it all in the computer when we're done, who was there. Somebody gets to track all this stuff. I'm glad it's not me.
He's coming in momentarily.
Thank you, sir. And isn't Hubbard over there at Foster's as well?
Let me go check on him.
Sorry, ma'am.
Okay, that's Erin Bridges.
Yes, ma'am. I apologize.
How are you this morning?
I'm good. I'm good.
Are we missing anyone else?
Yes, ma'am. Simpson and Hubbard. Chung or Hamilton, do y'all know where Simpson is?
Is Simpson not there?
No, he's in group 3.
He was probably told that he couldn't do it.
I know him. I just don't know what room he's in.
I'll go track him down.
There's
I'll have CQ make an announcement, ma'am. He's in our building.
okay, well, let's go ahead and get started because there was supposed to be some at 10:30, so maybe they were going to join the 10:30 group. Okay.
Yes, ma'am.
Yes, ma'am.
All right. So today we were going to do objective 1C and 1D. So 1C is basic facts about electromagnetic propagation. We're going to talk about different layers in the atmosphere and more specifically the layers in the ionosphere. And then we have a lot of definitions to go over, like what is reflection, refraction, diffraction, angle of incidence, atmosphere attenuation, multipathing, anomalous propagation, path loss, free space loss, and then we'll just briefly look at the transit. So the Earth's atmosphere, as you know from school, has got many layers in it. The only two that we really care about for RF communication is the troposphere, which is the lowest layer, and then the ionosphere. The troposphere is where all the weather happens. It goes up to about 11 miles above sea level, and it's got a lot of solids and liquid particles, dust particles, pollution, and moisture particles. And that's what scatters light, making it able for you to see sun rays. That's the layer where we live. and that's the layer that we use for tropospheric scatter. The tropospheric scatter normally starts about 500 megahertz, but it can start as low as 50 megahertz. Now, if you remember, we talked about tropospheric scatter previously, where you just, excuse me, you shoot your signal up into the troposphere at a high power. Because you have those small wavelengths, they get scattered back to Earth off these tiny particles, little moisture particles, dust particles, etc. And that was called troposcatter. Now the ionosphere, that's what we use for HF. It's called the ionosphere because it's ionized by the sun, by the solar radiation. Now, when it is heavily ionized, it will actually have three separate regions, D, E, and F. Uppermost region, the F layer, that's what we want to use for the long haul or long range communication, that beyond line of sight. So when the sun is up and there's a lot of ionization, we have the D layer, which is the lowest and the densest layer. Above that, you'll have the E layer. And then the uppermost layer is the F layer, and it will become more dense and actually divide into two separate layers, F1 and F2. It is this F layer that you want to use for that beyond line of sight communication, that long haul, 800 miles, 1,000 miles. Now, you're going to have, I just lost my train of thought. Oh, I got it back again. My train sometimes leaves the station, but it usually returns. Okay. Previously, we discussed that when you have high ionization in the daytime, at the lower end of your HF band has a tendency to get absorbed in this lower layer, so it cannot reach this F layer to give you that long haul communication. So in the daytime, when you have high ionization, the upper end of the HF band normally reaches the F layer and can be used. Lower end of the HF band has a tendency to get absorbed in the lower layers. And I see here that I have my D and E switched around. This one should be D, that one should be E. I'll have to correct that. So in the daytime, the higher end of your HF range seems to work better because it can penetrate the D and E layer to reach that F layer. That doesn't mean the D and E layer is totally worthless. Sometimes they're actually used for shorter distances. Now, a high end of your HF, though, will penetrate these lower layers to reach the F layer. Now, watch this. I'm very proud of this. As the sun goes down, the moon comes up, the D layer disappears, E layer thins out, and your F layer thins out. Well, when this happens at night, because the sun has gone down, now those lower end frequencies of HF can reach the F layer, and they can be utilized for long haul communication. Higher end frequencies without the D layer and just some sporadic E, when they hit that F layer, they can just keep right on going out into space. So at nighttime, the lower end of HF tends to work better. Now, I can't give you a specific frequency. All I can say is it's a reference. So if you're operating at, it's nighttime and you're operating on 20 megahertz and you start to lose it, then you're better off to try to go to a lower frequency. If it's in the daytime, then you would go to a higher frequency. Does everyone understand that?
Yes, ma'am.
Yes.
Okay, now at any particular time of day for any particular location, you're going to have a lowest usable frequency. That's exactly what it says. It is the lowest frequency that you can use where your distant end is going to get a usable signal. You're also going to have a maximum usable frequency, which is going to be the highest frequency you can use in your distant end, get a usable signal. Now, in between there, you're going to have your best frequency called the optimum frequency. It's usually going to be about 80 to 90% of that maximum. Well, again, this is all going to depend upon the amount of ionization and where you are, where they are. So there is no, I can't tell you, well, this is always going to be your best frequency. It's going to change. What's your best frequency at 2 o'clock in the morning may not be your optimum frequency at 8 o'clock in the morning because conditions change. Angle of incidence. Now, if you were to go up into the ionosphere and drop a plumb bob down, then you would have a straight vertical line coming from the ionosphere down to the ground. Now, your antenna is aimed up there. Your signal travels up to the ionosphere. And that angle made right there, can everyone see my arrow?
Yes, ma'am.
Okay.
Yes.
So that angle right there is your angle of incidence. Is the angle formed by a wave, in this case, our radio wave, striking a surface, which is the ionosphere, and a line drawn perpendicular to the surface at that point of incidence. So that is your angle of incidence. If your angle of incidence is too steep, the signal can just penetrate and keep on going. If your angle of incidence is too shallow, then it may just be kind of absorbed in the ionosphere and not sent back. You're going to have a critical angle. Critical angle is when the angle is too vertical for a particular frequency. And like I said, it'll just go right on out into space. Now, a critical angle for one frequency is not going to be the same for a different frequency. Okay. So if you go to for this particular frequency you're operating on, you're going to have a critical angle. If your angle is greater than that or more vertical than that, then you're not going to have any communication because you're going to lose your signal. So, reflection. Reflection is when your RF just bounces off a surface or an obstruction. You all know what a reflection is. You see it every day when you look in the mirror. That's a reflection. There is a law for reflection, and the law tells you the angle of reflection will equal the angle of incidence. Excuse me. So here is our straight line from the ionosphere to the Earth. Here is our RF going up to the ionosphere. So here's our angle of incidence. Well, the angle of reflection is going to equal the angle of incidence. Refraction is a change in direction of the wave due to a change in the medium it is traveling through. So here's our RF signal going up, and it hits the ionosphere, and instead of being reflected, it enters the ionosphere, and because of the ionization denseness, it's going to cause it to bend. And it's going to bend and eventually, hopefully, come back to Earth. Sometimes it'll actually bend the wrong direction. But that bending, as it goes through that different transmission medium, is called refraction. Like here, you can see it in this glass of water with the straw. The straw goes in, then it appears as if the straw shifted over here. And we know the straw really didn't shift over there, but it's the way the light rays travel through the air versus how they travel in the water. It causes them to bend, making it appear that the straw has shifted. Now, how much refraction you get up here in the ionosphere is all going to be dependent upon the conditions of the ionosphere, your incident angle, what frequency you're at. So sometimes if you're getting too much refraction, you can change frequency and correct it. Diffraction. Diffraction. Bending of a wave as it encounters a constriction or an edge, such as the side of a building or a mountain. Or you're walking down a sidewalk, everything's going along just fine, and then there's a part of the sidewalk sticking up 3 or 4 inches higher than the rest of it. You catch your toe on that, and the rest of your body tends to diffract face down into the concrete. That's diffraction, bending of a wave as it encounters a constriction or an edge. Okay. Longer wavelengths are more prone to diffraction, because they got more wavelength to get caught up on that edge of the building or that side of the mountain. Atmosphere attenuation is sometimes called atmosphere absorption. It's the amplitude or the strength of your signal is degraded by the conditions of the Earth's atmosphere. Now, the conditions of the Earth's atmosphere are continually changing. So sometimes atmosphere attenuation is worse than other times. The number one cause of atmosphere attenuation is moisture. Moisture comes in a lot of different ways. It can be clouds, rain, fog, humidity, anything. The moisture is the number one cause. Gases and random particles are also contributing factors. Tropospheric scintillation. This chart, here's your attenuation, and here's your frequency. It's showing you that as frequency increases and wavelength decreases, atmosphere attenuation will go up. So the higher frequencies suffer from atmosphere attenuation more so than the lower frequencies. Tropospheric scintillation. In the atmosphere, you're going to have random pockets of differing air pressure, humidity, temperature, gases, etc. Now, as your signal enters these different random pockets, it's going to react differently. Okay? It's going to speed up, slow down, refract. All of that's going to change your signal. All of that together is called tropospheric scintillation. It's the rapid fluctuation of amplitude or phase of a wave resulting from rapid changes in signal direction. And that's because as it enters these different random pockets, some of them will cause the signal to speed up because it's a less dense pocket. It enters an area of higher density, you want to slow it down or bend it. SHF and EHF are most affected by the tropospheric scintillation. Of course, it's going to be worse at lower elevations because you have more time in your troposphere. You also have more moisture and humidity, etc. Multipath propagation. When your signal leaves the transmitting antenna, it has a tendency to spread out. So when the signal reaches the receiving antenna, it hasn't all traveled a direct path. It's traveled different paths. Well, that's multipath. Well, the different paths are going to affect the propagation or the traveling of that signal. The part of the signal that took the shortest path will get there first. And then those that reflected a lot or just had to go through a thick grove of trees, they're going to come in a little bit different. Well, when they come together, you have this at the receiving antenna. It's the same frequency, but you can see the phases are different. The amplitudes are a little different. And when you combine those together, you end up with something that looks like this. Okay. Do you remember talking about an automatic gain control on the receiver of your radio in previous blocks?
Yes, ma'am.
Yes.
What was the purpose of that? Anyone remember?
Is to, I think, like modulate the volume so that if you're closer to the transmitter, if the recipient and the transmitter are close together, like as the recipient moves closer to the transmitter, it doesn't like increase volume.
Okay, no, I'm talking about on the receive end. On the receiving end, you also had an automatic gain control. And what its purpose was to keep your receiving signal constant.
Oh, I was gonna say.
Excuse me?
Oh,
Go
my
ahead.
bad. I should have said that. I was thinking that, but I just wasn't confident enough.
Well, then say it. I'm waiting.
Well, you just said it for me. It's to control the receiving signal and control like the how much you are getting, I guess you could say.
Well, as the signal coming into the receiver is not going to stay one constant amplitude. So if your signal coming in is stronger, it detects that and it sends a signal back there to turn down the gain. If the signal coming in is weaker, then it sends a signal back to increase the gain so that the signal going into now I just forgot, the multiplexing part of your radio remains constant. Okay, because it can't demultiplex it correctly. If it's up and down, you're going to have volume going up and down, and you don't want that. You want it to stay steady. So it's going to compensate for this turning into that. So as your received signal fluctuates, you have an automatic gain control that detects that and compensates for it so that it remains constant when it's being demodulated. Anomalous propagation. What's an anomaly?
Something strange or out of the ordinary.
Okay, so anomalous propagation is just variations in density, obstructions, variations in moisture, just anomalies, things that are different. So because your RF propagation path does not follow a straight line, again, parts of it are going to go through different anomalies, which result from variations in the density, different obstructions, moisture, gases, dust particles, etc. in the atmosphere. So reflection, diffraction, and refractions are examples of anomalous propagation. It's just different anomalies or differences. Free space. Theoretically, free space is a perfect space void of gravitational and electromagnetic fields. we just talk about free space, we're just talking more of a path clear of obstructions between a transmitting antenna and a receiving antenna. Such as here is a SATCOM antenna, and it's transmitting to a satellite. Well, you know you have to have a clear line of sight. So if you have a clear line of sight, the only thing between this SATCOM antenna and the satellite is space, correct? An area clear of obstructions. So that's free space. Well, I could have an antenna here and an antenna here, a direct line of sight transmission, and that in between them would also be free space. It's just space free of obstruction. Now, even though the signal is traveling to an area free of obstruction, you're still going to have free space loss. And that's because when the signal leaves your transmitting antenna, it starts to disperse, or it starts to spread out. Like a flashlight. When you turn on a flashlight, you can actually see the light start to spread out the farther out it goes. Okay? So that flashlight's going to have a loss in its energy just because the light spreads out. Same thing with your RF signal. When it leaves this antenna, it's going to start to spread out in a cone. The farther it travels, the more it spreads out. That's free space loss. It does not factor in any environmental conditions. It doesn't factor in any obstructions. It's just your energy spreads out as it travels. Now, you can see for SATCOM, you got a lot of distance for that signal to spread out. Therefore, free space loss is the major loss for satellite communications. Now, path loss, on the other hand, is anything that affects the signal. It factors in all environmental conditions and obstructions. Okay? Is the total power loss between the transmitting antenna and the receiving antenna. Now, it includes free space loss, which happens to be one of the most common losses, and atmospheric attenuation is another common cause. So free space loss does not factor in environmental conditions. It's just your energy spreads out. Path loss, it factors in all environmental conditions, including free space loss. Have you all used the transit yet?
No,
No,
ma'am, I
ma'am.
don't believe so.
Okay. I'm just going to briefly look at it because it's kind of difficult to explain it here on a slide without you having one in your hand. But at least this way you'll kind of have an idea of what it is. It's just a tool, and we use it to determine azimuth and elevation. Okay. Now, when you're putting up a SATCOM antenna, you're going to have to know what elevation, in other words, what direction does it need to point? And also you need to know, the azimuth, what direction. Azimuth is your side to side angle. And you also need to know the elevation, which is its up and down angle. So you need to know what direction to point it and how high to point it. So we use a transit. Transit will allow you to get the azimuth, which is measured in degrees. You have a 360-degree circle. An elevation allows you to get the up and down angle, which goes from 0 to 90. After 90, it starts going back down. You get to use the transit, you're going to see that it has two levels, a round level and a bar level. Ground level you're going to use when you're finding azimuth, because it's going to let you know when you're holding that transit level. And along with that, you have your needle. And just like a compass, a needle always points which direction?
North.
North.
Always points north. Okay? So if you want your antenna to point at 220 degrees, you're going to just hold this transit in your hand and you're going to rotate it until the needle says the north seeking needle is on 220. Then this is your sighting arm. That's the direction you'll point your antenna. Okay? And that little circle bubble just lets you know you're holding the transit level so that the needle can freely move. And your degrees are out here on this outer ring, 360 degrees. Elevation's a little more difficult because you're going to have to hold the transit sideways. Okay? And you're going to use this bar level. And inside the transit, have this inner scale, goes from 90, 0, back up to 90. You also have this movable scale here. I forget, it goes from 0, I think, to 30 or 60, I can't remember. But 0 is the only thing we're concerned with. The back of the transit is a little lever that you can use to move this. This actually will move back and forth. So that 0 on that movable part, you put it on the angle you want. Like if you want your antenna to point at 60 degrees, and you would move this until this 0 was on the 60. Then you would simply tilt the transit, the pointing arm, you would tilt the pointing arm up until the bar level said that it was level. The 0 or the bubble would be right there in the middle, and that would give you your elevation. So it's kind of difficult to explain here, but at least you see what it looks like. Any questions on what we covered? Everybody has it perfectly?
Yes, ma'am.
Hancock?
I don't know about perfectly, but yes, ma'am, I'll have it. I mean, the reflection, refraction, and diffraction. Yes, ma'am, I got those down for sure.
Okay, how about the rest of it? Free space loss, path loss?
Yes, ma'am, I understand those. I'm
Okay.
gonna have some fun times making flashcards today.
Oh, flashcards are great. Hamilton?
I'm good.
Chung?
I'm good, ma'am. Like I said, I probably just need to read over this again and maybe make some flashcards, and then we
Okay.
should be good to go for the test.
Okay, Londano?
I'm good, man.
Bridges?
I'm tracking, ma'am.
Okay. Now, tomorrow morning, we were going to go over the appraisals, correct?
No, ma'am.
Tuesday morning, ma'am.
Tuesday morning, I meant, sorry. You all don't want to come in on your down Friday?
We'd love to, ma'am, but we want to give you the day off too.
Oh, thank you. You're so kind. Okay, so we'll go on and do objective 1D then. Okay, can everyone see it?
Yes, ma'am.
Yes, ma'am.
Yes.
All right. RF spectrum interference resolution problem, or program, excuse me. Spectrum interference can be a problem, therefore you have to have a resolution program. Spectrum interference is anything that's going to disrupt your communications, or anything that disrupts the operation of an electronic device operating in the RF range. In other words, it disrupts your communication. It can be intended. It can be your enemies trying to jam you. It can be unintended. It could be from somebody doing something where they don't even know they're interfering with you. It can be from natural causes such as solar flares or the northern lights. The Air Force Spectrum Interference Resolution Program, the Air Force has a program for everything, provides you guidance on how to resolve those interference problems. Sometimes it's as simple as you look around and you can see your interference problem. I was way back in time when I was just a wee airman. We went on a deployment out to Las Vegas. And we had to set up two sites. One was down in the desert and the other one was up in the mountains. And when we set up the one in the desert, and then we drove up to the one in the mountains, got about halfway up there, we had to stop and put snow chains on the truck. Then when we arrived, we had to dig the snow out in order to get to the ground to put up the antennas. So we had two really nice extreme locations that we were working at the same time, one in the desert and one up in the snow. But anyway, the one in the desert, we could see down the road a little ways, there was a radar, and every time it would come around, it would interfere with our communications. So we could just look and see what was causing the problem. Now, it was just an exercise, so it was not a big deal. If it had been a time of war, we would have just blown them up and been done with it. No more interference problem. But sometimes it's that simple. You just can look and see where the problem's coming from. Sometimes it's not that simple. That's why you have this Air Force Spectrum Interference Resolution Program to provide you guidance. You want to try to solve the issue at the lowest possible level. There is one exception. If your unit is under the operational control of a combatant command, then you go ahead and you push it up the chain. You don't want people out there in the field without communication. Interference can be caused, again, by the enemy trying to jam you. It can be neutral or friendly forces. They may not even realize they're causing you a problem. Or it can be from natural causes. Again, solar flares, northern lights, lightning. So electromagnetic interference can happen inside the US or inside a host nation, inside friendly areas or inside enemy areas. It can be anything from complete jamming of your equipment to just an annoying hum on your equipment from a current. And two common natural causes are solar flares and northern lights, which the northern lights and the solar flares, they can cause radiation that can interfere with electronic devices. If you watch here, you see your little man walks through with his radio. Well, there we're going to have some interference issues. Most likely, this dish is going to override what he's putting out right there, because this is going to be much stronger. So depending upon the frequencies and the power output of these different transmissions, they can interfere with each other.
You're fine. I got my mic muted.
How do you resolve it? Well, you're going to accomplish the actions outlined in paragraph 3 of AFI 17-221. You're also going to contact your local installation spectrum manager. If the problem's not resolved, then it'll be pushed up to your MAGCOM spectrum manager. There is no one fix action because every instance of interference is going to be different. And you're just going to have to figure it out. Like I said, sometimes you can just walk outside, look around, and there it is. Sometimes it can be something more difficult to trace down. So, spectrum interference disrupts operations of an electronic device operating in the RF range. It can be from your enemy trying to intentionally jam you. It can be unintended by somebody else operating on a frequency too close to yours and interfering, or it can be from natural causes such as solar flares, lightning, northern lights. Resolve the problems by beginning with the actions in paragraph 3 of AFI 17-221. You always want to solve at the lowest level unless you're under the operational control of a combatant command. Wasn't that exciting?
Yes, ma'am. Ma'am, how would you know the difference between, or how would you decide if you were to troubleshoot that radio?
How could you determine whether it's intentional or unintentional?
Yes, and if maybe it's a part that's damaged, how do you know if it's like there's something wrong with interference or there's something wrong with the part?
Mr. Mayor, you still there? I personally have never had to deal with an interference problem that I couldn't just look and see what it was.
Y-
So, Mr. Mayor, can you help us out here?
Okay, what was the question again? I was busy.
I was saying, I know there's a troubleshooting method whenever there's a problem with the radio. I was just asking, how would you know if it's a problem with interference or a problem with the part of a radio?
Well, I know it's going to sound strange. But what you do is, okay, with a radio, you're going to look at it. Okay, am I getting this just solely on this radio? You're going to have a network of radios too. Everybody's going to be on the same frequency. All right, so that might be the issue. If it's just only happening on one radio and not many, then you know it's not an interference issue. It's a radio issue. But if it's happening on all the radios, and I've had this experience before at Hill Air Force Base, it ended up that it wasn't enough interference to prevent communications. It was just annoying. And it would just sound like a ch, 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 ch. And it would come and go. Well, it took us about 2 years because of how intermittent it was. We finally narrowed it down that it was between that August to October time frame. And we finally got it to where it would stick around for a while, and we went out with location antennas, and we figured it out, after about 2 days. It ended up becoming mountain goats on one of the mountain passes that had GPS collars on them. So we had to get with the Fish and Game people and have them transport those goats farther north. So that was a frequency interference of a friendly kind, but it was interference because it was going over 3 different nets. One was the fire department, one was the police, and the other was the ambulance services. So it did have some problems when they were trying to communicate, because there were times where you just couldn't get the communications over that noise. So that'll hopefully will give you an idea of what's happening out there.
Yes, sir.
Okay.
It's very interesting.
Yeah.
I misunderstood your question. I thought your question was, how do you determine whether it's intentional or unintentional?
That was my mistake. I should have been more clear.
So, but now I want to know, Mr. Mayor, how do you determine when you're getting interference, whether it's intentional or unintentional? I guess you just have to find it and then you'll know.
Yes. Well, we had with our frequency managers that were on the spot, they were the second level in trying to troubleshoot this at the lowest possible level before we started running it up through MAGCOM, because we were getting ready to install a trunking system and we didn't want any type of interference. Whether in this case it was an accidental interference because the goats were supposed to stay up in the Idaho, Montana area. Well, I guess they didn't get the memo and just jumped the fence and came down around the Utah area. So, hey, what can I say about that? And
You're stubborn.
yeah. Well, it's one of those, we thought it was unintentional because there was a lot of things around Hill Air Force Base. There wasn't any intel on anybody that was trying to intercept. So, taking out 2 Yagi antennas and trying to find the strongest signal, and we finally located it in Ogden up on one of those mountains. So, happens.
Well, that's interesting. Interference by goat.
Mm-hmm.
Anyone else have any other questions?
None that I can think of.
Okay, so we were going to meet Tuesday at 8 to go over the appraisals. Is that correct?
Yes, ma'am.
Yes, ma'am.
Are we meeting
Okay.
again later? Because I know that me and Lindana, Hamilton, and Simpson have lab Tuesday morning.
Yes, we have one at 8 and one at 10:30
Yes,
on
ma'am.
Tuesday. Does that work?
Yes, ma'am.
Okay. So I'll see some of you at 8 o'clock on Tuesday and some of you at 10:30, and it's specifically to go over the appraisals, answer any questions that you may have, because you test on Wednesday, correct?
I believe it's Thursday.
Okay. Well, then that'll give you an extra day in there to study.
Do we already have the appraisals?
It's next Monday. It's not next Monday, but the Monday after that. It's 8-day block, right?
Okay, but
May I
have you
interrupt?
completed the appraisals?
The question was, if I'm not mistaken, they didn't have the appraisals. Did I get that correct?
I don't have one.
Or can we download it?
Miss Irwin, is it
I believe-
put into their resources by any chance at the top of?
I just checked.
I can check real quick.
Okay. If it's not, we can load it in there.
I haven't ran into this before. The other classes have had them. I don't know if the lab instructor gave it to them.
Well,
Or
we
if
can
it's
load it
loaded.
into their resources, which is at the top left of the page. We'll have
Okay.
to scroll up there to put it in if we.
If it's not there, then you'll load it.
I can, yes.
Okay. Mr. Mayer's the SME for Block 4, so he can do that.
Well, if you had them, you could do the same too. So.
Okay, I didn't download those, but I can. Actually, let me see here. I think I do have them. Appraisals, okay.
Do me a favor and check 1 Delta
Okay,
appraisals, and I want to see the last question.
all right, I'm pulling it up.
You watch it; it has all the answers on it, because it says
Yeah,
answers.
yeah.
Yeah, go down to the last
Don't-
one. Go down to the
Don't
last
look
one.
at it. Just close your eyes.
Whoa. Okay, good. That is the correct appraisal because of the AFI
Right.
17221. Okay, you can click out of that.
Okay, so I don't have the blank appraisals. I have the appraisal key.
Okay, I'll try to get that to you as far as the regular ones, so that way, just in case someone can't find them, you have a copy of them.
Okay.
Yeah, I don't believe we have them.
You do?
No, sir, I don't think so.
Okay.
I looked.
All right. We'll
How
try
do
to.
I
Go ahead.
how do I load them in there?
Well, you don't want to load those.
Oh, not
But-
mine.
Yeah. What you would end up doing is you would highlight all of them. You know, you could do a shift all the way to the top there and drag right into block 4 resources. It's
Okay.
that simple.
Okay. I can do that.
Are you online as in can get into the InDrive?
No, I have
Okay.
to get out of Discord and then go back in and get on the VPN,
All right.
get them, download them to my desktop. Then
Okay. Geez, I got to look real quick. Anyway, wrap up your class.
okay.
And I'm looking.
Okay. All right, class. I'm going to go and get those appraisals and I'll put them in the block 4 resources. It will take me a few minutes to do it because I have to log out, log in, shift things around. So give me about 10, 15 minutes and they should be in there.
Stand
Okay.
by a
Yes,
second.
ma'am. Thank you so much.
Thank you,
Okay.
ma'am.
I think I might have them already. It looks it. Let me see if this is the correct one. Oh, it is. Give me a second and it'll be loaded. I gotta minimize. Let me stop this too.